He's currently a PhD student in computer science, and he's going to tell us about how to use Julia to study this causal discovery.
Use this one, right? There we go. All right. Good afternoon, everyone. I'm Sepehr. I'm a PhD student at EPFL, and I'll be talking about recursive causal discovery with Julia. So first, I'm going to be talking about what causality is overall. Then I'll talk a bit about causal discovery, and then more specifically about recursive causal discovery, and then my package to do recursive causal discovery in Julia, and then finally I'll conclude the talk. So what is causality? To answer that question, I'm going to say what causality is not, and that is correlation. Causation is not correlation. And I'm sure many of you are familiar with this website, Spurious Correlations, that goes and finds two things that are correlated that have absolutely nothing to do with one another. So one of the examples that I found here is the distance between Saturn and the sun correlates very strongly with an R-squared of, I think, 0.9 with Google searches for how to make a baby. And maybe there's something that I don't know, but I don't think those two things have anything to do with each other. So correlation, causation in general is not causation is not correlation. In fact, causality is the relationship between a cause and an effect. So something is causing some effect. So I have a little example here. It's we're looking at the income of an individual, and the income is an effect of their education level. So y is an effect of x, and we see that little directed edge, so it's represented by the graph. It is also an effect of that person's parental socioeconomic status. And the parental socioeconomic status is also causing their education level, right? Because the parent chooses what school to put their children in. And of course, causality has many, research. It's used in many applications, right? Such as public health, education, or policy making. And in general, when we want to represent these causal relationships, we're using causal graphs. More specifically, we're using things called DAGs, so directed acyclic graphs. So the directed portion means that we have these directed edges. Acyclic means we have no cycles, and the graph is, well, we have a set of vertices and edges. So an example is like this. So x1 is causing x2 and x3, and we would say x3 and x2 are the effects of x1. And a key question that arises often in research is, what happens if we don't know the graph, right? So we know these variables exist, but we don't know the causal relationship between them. And we want to learn that through data, and that's where causal discovery comes in. Causal discovery, or sometimes also called learning Bayesian networks, is the process of inferring these causal relationships from data. And so, for example, we have some observational data, x1 through x5, based on the example that I showed previously, and you want to learn the relationships using this data. And a common approach is this algorithm called the PC algorithm. It was developed in the year 2000, and basically the way it works is it tests each pair of variables for their conditional independency. So basically it checks whether x is independent from y given some set z, and it does this for every single z essentially, and then if it turns out that x is independent from y, we know that there's no edge. So neither x is causing y nor y causing x. And then it does some orientation. These details don't matter. What matters is the learning portion, so learning the skeleton, is very, very slow. And it's slow because it has to test every single pair of variables. And in fact, it has an exponential complexity. So this is very, very bad if we have a lot of variables. And that's where recursive causality comes in. So recursive causal discovery. So in recursive causal discovery, the idea is to reduce the size of the graph at every iteration of the algorithm and then recursively learn the graph. So the way it works is we want to identify what we call a removable variable. And the definition for what a removable variable is technical, it doesn't matter. What is important is that a removable variable can be removed from the graph without affecting the graph too much, essentially. So we find a removable variable using these conditional independency tests. We learn its neighbors, and then we remove it from the graph, and then we repeat step one. So we keep finding removable variables, learning their neighbors, and removing them from the graph. And I have a little example here. So on the left, we have the variables that we're working with. On the right, we have the learned skeleton so far. And so we first identify x5 as removable using those CI tests. We learn its neighbors, so x3, x4. We remove it. We identify that x4 is now removable. We learn its neighbors, x1, remove it. x3 is connected to x2 and x1, remove it. We move on to x2. And then x2 is only connected to x1. And then once we only have one variable remaining, we're done. And so there are 4 of these recursive causal discovery algorithms. And I want to bring your attention to the number of CI tests that they're doing. Just the most important thing is PC, the algorithm that I said is the most common approach, needs an exponential number of tests. And these algorithms, under certain conditions, don't. The worst case is still exponential, but for certain structures, for certain side informations that come with the graph, these algorithms are going to perform much fewer number of CI tests. They're going to be much faster. And so we implemented recursive causal discovery in Python called RCD, and we implement all the 4 algorithms, and you can install it as such. But we don't care about that here, right? Because we're at JuliaCon, we care about the Julia implementation. And it just so happens that the Julia implementation is much faster than the one in Python. So we implemented in Julia. We look at the time it takes as a function of the number of variables of the graph, and we see that it's around 2 orders of magnitude faster. This is on the log plot. So it's, in fact, 150 times faster. And the way it works, of course, it's on the repository, so you can install it. And all you need to give it is a data matrix, right? So you can read it from CSV, or you can load the matrix some other way. You give it the data matrix and some CI tests. So here I'm using some Fisher Z test. It's for Gaussian random variables, but you can use your own custom test. You give the data matrix and the CI test, and then it returns you an undirected graph, which represents the skeleton of the causal graph. And if we compare it with this PC algorithm that I was talking about, we see that. So first, we're going to look at the F1 score. F1 score is essentially a combination of recall and precision. So the higher it is, the better the algorithm was able to learn the graph, right? So we see that RSL, it's one of the RCD algorithms in blue. Even by 200 variables, it's around 80%, right? 0.8 F1 score, whereas PC is lower at 0.6. And of course, in terms of the number of CI tests, it's PC is doing much more CI tests, so it's much slower compared with RSL. And as for future direction, we want to implement the other algorithms, because so far we only implemented RSL. There are 3 others. And then we want to add more CI tests. Right now, there's only Fisher Z test for Gaussians, and Pearson partial correlation. And of course, we want to potentially integrate with causal inference JL. It's one of the popular causality packages in Julia. And with that, I conclude my talk. Thank you for listening, and I'm open to questions.
Thank you. Any question? Yeah.
Hi, thank you for the talk. Wouldn't this be a Bayesian network that you're
Essentially,
finding?
yeah. You can also, in some literatures, it's also called Bayesian network. So in that case, you would say learning Bayesian networks instead of causal discovery.
Yeah, why would you say causal?
Because it's a causal graph, right?
Wouldn't it be a Bayesian graph, not a causal graph? Because every causal graph is a Bayesian graph, but not vice versa.
Bayesian networks don't give you the correct direction of the edge. So in Bayesian
Right.
networks, you can also... Oh, you mean in terms of that?
Exactly,
Yeah, I mean, so...
because you can't find both ways if it's a chain left to right.
Yeah, so technically, so I had this Meek rule step, right? Where is it? Yeah, here. So technically, you can learn some of the directions, right? So technically, in the end, what you get is a partially directed graph. So some of the edges, you know the directions of, some of them you don't. So in that sense, it's still, I mean, you're still trying to learn the causal graph. You just can't learn it fully. You can learn it up to an equivalence class, essentially. And what are the problem sizes that you can kind of work with? Let's say an hour of compute. An hour? I would say on the order of thousands, probably hour, yeah. Hour should be on the order of thousands, yeah.
Okay, one last question before we move on to the next talk.
Hi, sorry, maybe this is just like a different field, because so from physics, causal is like, time ordered, like what happens
Mhm.
before, what happens after. How do you generate the synthetic data set? And like, I guess, yeah, how would you, if causality is like the main as part of this, then it appears that the meek rules
Mhm.
part should be the most important. So yeah, I was just curious as to how, like, because the CI tests are, well, that's correlation, not causation, right? Like classic thing. So
Yeah. So I'll start with the second part of your question. So the meek rules part. So this part is not it's not doing any learning. So all the learning is done here. That's why I focused on learning the skeleton. That's the part that's actually dealing with the data and then using these conditional independency tests to determine whether an edge exists. The meek rules, it's just using certain assumptions that are placed on the graph, right? Because we know the underlying graph is causal, like we're making that assumption. There are assumptions on like the Markov property, faithfulness, so we're assuming those properties, and when you assume those, it turns out that you can orient some of the edges. So this is just like a deterministic algorithm that you go through and do. So there's no learning done here. And as for the first part of your question, so the general model in causality, it's structural causal model. So you assume if you have like, let's go to a graph. If I have something like this, I assume that x2 equals some function f2 of x1 plus some epsilon, where epsilon is some noise, right? And you don't know, well, either the noise or f. So that's where the causality comes from. So the children, so nodes are only dependent on their parents. So that's where the causality comes from. So in the simulations that I showed, the noise is Gaussian, and the functions I think I took linear functions, yeah, with changing coefficients, yeah.
All right, thank you.
Thank you.